So let's continue talking about model of execution, what's happening on the stack, what's happening on the heap. And for lecture questions, it's really hard to write a question that's quizzing you on the stack and heap and drawing the memory diagrams and stuff. So the lecture questions, they're focusing on references, specifically on Mondays, Fridays. Next week in lab, that's where you can expect to draw the stack and heap diagrams. I'll give you some code, the TAs will give you some code, and say, as this code is executing, what's going on the stack, what's going on the heap, and how does all that represent it in memory. That's where we can assess you on that third bullet point. For the lecture questions, it's most of those first two, unit testing and references, writing methods with references. How do these methods work when they are working with references? In today's example about heap space is going to show more reference examples to hammer those points home. So this lecture question, write 3 classes in the execution package. The first class, just a class named valuable, which will represent some valuable item with no known properties, at least in our programs. It has no constructor parameters, it has no methods, it has no state variables, nothing really known about these variables. It's just an object. And the main part of this assignment is, how do we work with this thing? We have nothing to check. How are we going to write some testing that works with an object that has nothing for us to test? That's one of the big things we want to talk about for this one. A class named trader, which is going to represent a person who has one single valuable item, just one thing. They take it in as a parameter of their constructor, and this variable has a type item. So this does have a clearly defined name. It has to be named item, so we can use this in our testing. So in your testing, you can say, create this trader1 dot item, assert that equals something. You can do things like that. Item is defined, the name is defined, it has to be item. You can count on my code on Autolab having that name item. That name will be item. It'll be of type valuable, and it'll be var. It'll be variable. There's no and. Just that variable. The trader doesn't have any methods, no other state variables other than that one item. It's just somebody who has an item that they want to trade, some valuable item that they're willing to trade with other people, with other traders. And then a class trade agreement. So 2 traders can enter into an agreement to trade their items with each other. To do that, create a new trade agreement. This is going to have a constructor that takes 2 traders and one method named execute trade, which will, as the name implies, execute that trade between the 2 traders. So 2 traders enter into an agreement when you create a new trade agreement object. And then when you call execute trade, they're going to take their items of type valuable, and swap them with each other. And this is important that we do this by reference. We want to make sure that we're trading the references of those objects, because there's no real properties to check of those valuables. If there were, say we had a name or a price, we don't want to make sure that after the trade, this trader has a valuable with the same name and the same price as the one that originated with the other trader. We want to make sure that they have the exact item, that exact instance. We don't want to just say, okay, they have a diamond with the same size and the same value and everything. No, it has to be the same value. So we're going to check that by reference. Do they have that exact same item that the other trader had? And does the other trader have the exact same item that trader began with before the trade was executed? So we want to swap those by reference so they refer to the same object on the heap. This trade can only be executed once. They enter into an agreement, they execute the trade, and if you keep calling execute trade after that, nothing happens. So you can't enter a trade agreement, execute trade, swap the items, call execute trade again, swap back, and back, and back. It's not how trades work. They enter an agreement, they execute the trade, and that's it. It's over. Call the method again, nothing should happen. So a little extra functionality there. And then the test, unit tests to test this. Create some valuables, create some traders, create trade agreements, execute the trades, and make sure that the traders have the correct valuables at the end of those trades. So to do this, one note, if we use the equal operator, by default, this is going to be a comparison on references. So those variables of type, in this example, a variable of type valuable is going to store a reference to that valuable. And in this case, if we have 2 variables and we say, are these equal to each other using the equal operator, it will tell us if two variables of type valuable refer to the same exact object. That's the behavior we'll get from equal equal. So if we want to check, does a trader have the correct variable in its item variable, we're going to take that item variable and say, is this equal to the original item that I'm checking for? That'll check by reference. It'll only return true if those two variables refer to the same object on the heap. So that's how we can check to make sure each trader, after the trade is executed, has the proper valuable as their item, as their one item. If those two variables store different references, it'll return false. So even if we had values for the variable, for the variables for the valuable, if the valuable had like description, price, I don't know, quantity maybe, if it had a lot of state variables and we had two variables with all of the same state variables, and we said, are these equal to each other with equal equal? It'll return false if they refer to different variables, even if they had all the same variable values. It's a lot of V words there, but even if it had all the same values. Because the equal equal by default, unless we tell it otherwise, which we're not yet, we'll do that in the next couple of weeks. If we don't tell it otherwise, it's going to check by reference, do these two variables refer to the same exact object on the heap? And that's what we want to get at, obviously, talking about references throughout this whole question. Any questions on the question itself? All right. So last time we saw a couple memory examples. We talked about the stack and we talked about the heap. And we gave kind of quick examples of both. Today, I want to do the same thing, but go through more in-depth examples. Last time we created one object, put it on the heap, passed the reference to it to a method, and then that method modified the state of that object on the heap. And we saw that change in main even after the stack frame was destroyed. With the stack, we saw a few stack frames being put on the stack. Actually, just one stack frame being put on the stack. We entered in a loop that created a new scoping. When we entered that new block of code, we had different variables, kind of a different environment. And then that was destroyed, the stack frame was destroyed, went back to the main stack and ended the program. Today we're going to see examples showing the same concepts, but getting a little more in depth, driving these points home a little bit further, and seeing how more complicated examples work. So, multiple objects on the heap, multiple frames on the stack. We're going to start with the heap example. So let's take a look at this example, which fortunately is getting a little dated, but the movie's a little old. But we're going to see this example. We'll walk through it in the code. I'll do a quick overview now, but we're going to step through this line by line and look at the stack and heap and how everything's stored. So for this, we have a class named bird with a couple of state variables, a value and a variable technically. One method. We have a box class that's going to take two birds in its constructor and has one method. Then a main method, which is going to work with references of these types. And we're going to see how each reference is stored in heap, how we have those references, how we pass those references, etc. So let's set up our stack and heap. We start our program, ask our operating system for some stack space. So our stack up here gets our command line arguments, and we're going to start putting values here, and then our heap space over here each time we need more heap space from the operating system, new chunks of our instance. So let's just go through this line by line and see what happens. Trace through the execution. So the very first thing we hit is this new bird. We want to create a new instance of the bird class, a new object of type bird. So we're going to create that new bird. Every time we call new, this keyword new is going to ask our operating system for enough space on the heap. So anywhere, wherever our operating system decides, but enough space in RAM that's going to be able to store a bird. So we need at least room for 2 ints to be able to store this bird. We're going to get that space from the operating system. And the operating system is going to return to us a reference and say, okay, I gave you space. Here's where you can find that space. Our program creates those two variables, writes them down, and then we get that reference. So when we create this variable bird, or this value bird of type bird, we're going to store just that reference. How can we find that object of type bird on the heap? So that reference tells us how to find this somewhere in RAM. Remember the heap space, we don't know where that is, we don't care where it is. We just know that through the references, we have the ability to find that object in heap space, somewhere out there in heap space. Next thing, we saw this last time, we're going to create a variable, assign it a value, that's going to go on the stack, technically. I didn't talk about strings last time in class, and I'll give you the warning, technically we are going to handle strings a little bit wrong. The strings technically would go on the heap, but the way that they behave, because they're immutable, they will behave as though they were on the stack. So for our purposes as developers, when we're coding, if we pretend strings are on the stack, we can get away with that, and that's the way they will behave. We won't really have any reference behavior with strings, even though they are technically on the heap and passed by reference. So if you want to put those on the stack, next week in lab, you put your strings on the stack, you're not going to be penalized for that, it's perfectly fine. If you do want to do the technically correct thing and put them in heap space, that's fine too. If you do put them in heap space, I don't want to go down this rabbit hole too much, but you would have to put the string in the heap, then allocate another piece of heap space for the char array that it stores. So you'd have two different pieces of heap space created. Gets a bit messy, just drawing things, just fitting everything on the slide. If you want to pretend they're on the stack for the purposes of this class, I'm okay with that. Other professors, they might say, no, this is how they're actually represented. But just to get that disclaimer out there, I'm going to pretend strings are on the stack and pass by value. I'll pretend that they're like that, because that's the way they behave. All right, with that, we hit our first if statement. We have a new block of code, so we're going to start, we have to resolve the conditional first. So we're going to start a new stack frame for this in danger call. So at this point, we're going to go to the bird variable or value. We're going to go to the bird value, use the dot operator, which is take your reference and follow that reference to wherever it points to, wherever it leads you to in memory and heap space. Access that object and call this method on that object. So with this object here, we're calling the in danger method. That's going to access times checked, and I should have added this. I could put this dot times checked just to make it clear that this is a state variable that I'm modifying. So I'll go to times checked. Since I'm calling this from this object, the reference of this, or when I leave it off, the variables that I access, are going to be the variables attached to this object, the calling object. And this is always a reference to that calling object, whatever object was accessed through the dot operator. So when I go to times checked plus 1, this times checked variable is going to increment by 1. I'm going to return true, and I'm going to enter, this results to true, and I'm going to enter my if block. So I have a new block of code. That stack frame is destroyed. We're done. That method returned its value. And we start this if block. We start a new block of code. We're going to create a new value named action of type string with the value panic. Put that inside the if block. And then the very next line, we hit the end of that if block. So guess what? That variable we just created named action, we destroy it. So since we created that variable inside that block that just ended, that variable's gone. And then when we get to print action, since this variable was destroyed, and when we referred to action inside this block, this is a completely different variable than this action. When we assigned this to panic, it was assigned to this new variable and never affected this variable out here named action. So when we get to this print statement, we're going to print nothing. Even though it would seem like we assigned action the value panic, that change was made on a different variable named action that was destroyed at the end of that if block, and now we're reverting back to this action, which was never modified. Which was never modified. So this variable is never modified. We print out nothing when we get to that point. because of the way the scoping works. We created a variable with a name that was already on the stack, but we created it in a different scope, in a different block of code. So it was a completely different variable. Now we get to this next line. This next line is a mouthful. Spend a little bit of time here. So we have this assignment operator. We got quite a bit of stuff going on, and let's just piece it apart. We have a variable we're going to create eventually that's going to be assigned the return value of this new call. This new call is going to create a box that takes a bird and also creates a new bird. So this is where we have to start. If we want to resolve anything, we're going to start with this, creating this new bird. So we're going to say new bird. That means we're going to call this constructor. It doesn't take any parameters. We're going to create these variables. We're going to ask our operating system for space to store this object. We're going to get a reference to that space in memory. And that's where we're going to store those two variables associated with this object. So this object has those two variables. And these variables have the same name, but they're completely different than these two variables. They were created in different scopes. They're in different spots in memory. They're completely different variables, even though they have the same name. We don't care that they have the same name. They're completely different. So when we follow this reference, we're accessing these two variables. When we follow this reference, we're accessing these two variables. So we created a new bird. We created a new box also. We gave it this bird from this variable, which is storing 42,976. That reference to this bird, which again, the numbers I just make up just to signify that these are in different places in memory. We don't know or care where they actually physically are on the RAM sticks. But this reference, we're giving it as the first argument of the box. So that goes in bird 1 through all these, chasing through all the code. That's where we got it. And bird 1 has this reference, refers to the same bird as that variable bird in the main block. The second bird, we got some other space, some other reference the operating system gave us. We're giving that to the second bird, bird 2 in this box. But with this one, notice that this bird can only be accessed through the box. If we do box.bird2 somewhere in main, we can access that, but we actually don't have that bird anywhere on the stack. Nothing on the stack directly refers to that bird 2, but we can still create a reference to it. We can give that reference somewhere to that box. We just never happen to store it in a variable in main, and that's perfectly fine. We just created a new bird and directly gave it to the box. So that reference only appears right here, and that's the only way we can access this bird object here. Then we create that variable box on the stack and give it the reference to the box that we created, that we just created. Yes?
So if you needed to change something with the second bird that you made without any direct reference, could you do that? There's no way to actually access it.
Yes. So after this line, so how would we make if we want to make a change to bird 2, how would we do that? We could do box.bird2 and access it like that. So we have a reference to the box right here. So we can say box dot, which means follow your reference. Follow your reference over here. And now once I'm inside this object, then I have access to bird 2. I can do dot bird2, box dot bird2 dot, meaning follow this reference. And then I can access this bird. So at that point, I'm inside of this object. And then I could do something like times checked equals 10 and modify it from there.
So it's automatically named bird 2?
It's named bird 2 just because that's what I named this variable here. But it could be named, the name never, well, it kind of does show up in main. But just because I named it that in the constructor. Question?
That was my question.
Yeah, just because that's what I named my constructor variables. So those become, once I create that object of type box, that's what these variables end up being called. Same with the birds, times helpful and times checked. That's what those variables ended up being called, just because that's what they're named in the class when I define the class. Just like in the lecture question, when it's going to take in its constructor a valuable named item. So then you can say trader.item to access that valuable. You can access that directly, or indirectly rather. So I have box on the stack. that with a reference pointing to this object of type box, which has two references pointing to my other two objects on the stack. So all these objects are semi-associated with each other. The box has references to the birds, but they're kind of loosely associated in memory. They can be scattered all across memory, however our operating system decides to handle our memory, or the JVM decides to handle our memory, and they can follow those references to jump around and access those values, those variables of each other. Any other questions? All right. So now we get to our next line. We have a method call. We're going to put some frames on the stack. I'm not going to focus on the stack frames too much in this example. This is the next example. That's what we'll talk about pretty much exclusively. But we will put two frames on the stack. We're going to call box.inDanger. That's going to create a new stack frame. We're going to access box. So we're going to this object. We're calling the method from this object in danger. So bird1 and bird2 are going to refer to the bird1 and bird2 of this object, since this is the calling object. Then we're going to call bird1.inDanger. We're going to follow this reference, call inDanger from this bird, call this method, and access this times checked value. Increment that by 1 and return true. So we use references just through box.inDanger to be able to follow those references, jump around the heap, to be able to call those to see what object is calling which method. So when we call that, times checked here is going to increment to 2. Even though we never really accessed the bird at all from main, since we called box.inDanger and then box access inDanger bird1 and that access times check, we end up getting that change made to the heap. So even though we didn't do anything with bird directly, bird refers to the same bird, that variable changed in that bird variable because it was changed through the box, through that kind of chain of references. Then the same thing happens with bird2. We're going to call bird2.inDanger, follow this reference. That's this object. That times checked is going to increment, and then return true. We're going to return true and true, so we're going to return true, and this will be true. So after all that, we have a few changes on the heap, a few changes to our objects in heap space. Return true. That means we're entering this if block, start a new block, and this time when we access action, we're not declaring a new variable. We're just saying set the value of action to this value. So now our program's going to look inside the if block on the stack, not find any variable named action, expand it, search. It will find a variable named action outside of that scope. It has the value nothing. We're going to overwrite that with stay in the boat. Exit that block. There were no variables declared in that block, so nothing's really destroyed. Then move on to the program. Now when we hit this print line, that action was in fact changed, and we're going to print out stay in the boat this time. End of our program. Free up all the memory. Any questions on this example? Any more questions? Kind of a lot. I go pretty quick through it, so let's take some time to digest that question.
Yeah, so once the program ends, then just everything gets destroyed.
Everything,
So the heap is what is holding more, or it's less temporary. The stack is more temporary, the heap is less temporary, that's all.
Yes. So the heap is, at the end of the program, all memory is destroyed, the stack, the heap, everything's freed up. The heap memory is more, we tend to call it volatile, it's more dynamic is the word. Dynamic. So I didn't show it here. It's a little outside the scope of this class, but we can give back heap space during a program. In fact, it happens quite often. If we don't have a reference to an object anymore. So for example, if if after this right here, I said box equals new box of, I don't know, bird, or whatever, but reassign the value, I would have to change it to a bar, of course. But if I change box and assign that to a new box, and nowhere in my program do I have any reference to this box anymore, this box will be freed back up. They'll go to another program. It's not ours anymore. This is what we call garbage collection. And when we have an object in heap space that we don't have any references to anymore, the JVM is going to see that. It's going to notice that we have no way of accessing it anymore and free up that memory for us. So we can lose heap space as we go. And in fact, that's a good thing, or else we use a lot of RAM that we're not actually using. But we can't lose any stack memory until the program ends. That's our memory for the entire lifespan of that program. Did I get your question? Any other questions on this? Moving on. So that was multiple objects in the heap, in heap space. Let's talk about multiple frames on the stack. And I mentioned this a few times, worth repeating. Just to make clear the expectations, we're going to look at a recursive method here. And I expect you to be able to follow along today's lecture, especially when I'm walking through you step by step. I do not expect you to be able to write recursive methods at this point. It's a topic for later in the course. If you're a little bit wondering what exactly is going on in these recursive examples that I show, it's perfectly fine, it's perfectly normal. Recursion takes a while to really wrap your head around. It's kind of a slippery topic to really grasp. And that's exactly the reason why I want to show some recursive examples early. I just want to give you a light taste of it before I'm really expecting you to get these things. Then later in the course, when I'm saying write recursive methods, it won't take us as long to ramp up to that once you're used to seeing at least a couple of these things. That and the recursive method fits a lot better on the slides. If I want multiple frames on the stack, I don't want to have to write 4 methods that all call each other. So there's a practical concern here too. But let's call this method. I'm going to compute the geometric sum of 3. I'm going to do that through this recursive method that's going to call itself. So let's trace through the stack and see what's going to happen on the stack when we call this method. So the very first thing is a method call. The very first thing we do from inside the main stack frame is create another stack frame. Another stack frame, we got 2 already. So we're going to create a stack frame when we call this method. Every time we call a method, we're creating a new stack frame, which is an isolated environment on the stack that can't see anything, can't access things outside of that stack frame. So we're basically almost starting a whole new program for this method call. So we create a new frame on the stack. We create a variable for each parameter. There's just one in this case. Create that variable, assign it the value of the argument. So we have our parameter equal to the argument. Put that inside the stack frame, and then start calling the method. This entire method is one conditional that's going to decide what we're going to return. In this case, 3 is greater than 0, so we're going to run the if part of the conditional. Very first thing we do after that's true is create a new frame and put it on the stack. So we created a stack frame, created a variable for the parameter, entered an if block, so we're in a different scope, and then created a new stack frame right away. At this point, and created a new variable for that new parameter. At this point, we already have 2 variables named n with 2 different values, both on the stack. But since they're in different stack frames, that doesn't concern us at all, that doesn't bother us. So we have 2 variables named n, but since we're inside this stack frame here, we can't even see this variable n. So we don't really have scoping concerns. We don't have to worry about, okay, where are we going to search for these variables? If I say n, what n is it? It's always going to be this n. This is why we don't really worry about when we write methods, what we're naming things, what we're naming our variables for this concern anyway. So for example, if this were not the behavior of stack frames, and I had a variable n, and I also had a variable n in my main method, we could start having naming conflicts and having some kind of disastrous effects in terms of that. Since this is a new stack frame, a brand new environment, doesn't matter what I'm naming my variables. Especially if, say, somebody else is calling your method and you don't know what they name their variables. We don't want to have to worry about that. Stack frame solves a lot of those problems for us. So new stack frame, n equals 2, call the method again, conditions true, new if block, new stack frame, new n, new value for n. N is 1, conditions true, new if block, new stack frame, new n, new value for n is 0, and we have 1, 2, 3, 4 variables named n, all with different values, all on the stack. No concerns because they're all in different stack frames, so they're not conflicting with each other in any way. Now n is going to be 0, and we're going to hit what's called the base case of our recursion. So if this just kept going, we'd get in trouble on this one. But since we have a base case, which is some condition where the recursive method does not call itself, that's where we find to start returning things. So here, n is 0, 0 greater than 0 is false, hit the else, and just return 0. So this stack frame is going to be destroyed. We're going to return 0 and return back to the previous stack frame. So we're going to destroy this stack frame, return 0, return to this stack frame, and we're going to pick up execution exactly where we left off. So in this particular stack frame, we were waiting for this method call to return. So we created a stack frame for this method call. That stack frame was just destroyed and just returned. So we can pick up execution right where we left off. So this returns 0. We create a variable named result, assign it the value 0. Result plus equals n. We have to look for an n, look inside the if block. We don't find one. Expand our search. We find it right here. We use this variable n on the stack. Even though we have 3 variables n on the stack, we got to use the one from inside this stack frame. It's the only one we have access to. So result is going to equal 1. Return result, which destroys this entire stack frame. This returns 1. Now this stack frame, we resume execution. That was on this call. That returns 1. Result is 1 plus n. N in this stack frame is 2. So we get 3. Return 3. That destroys this whole stack frame. This one is now returning, because this is the last expression in the method call. Destroy this one, return 3. We return to this stack frame, this to resolve. This results to 3. Resume execution. Result equals 3. This value for n is 3 in this stack frame, so we have 3 plus 3. We get 6. Return 6. Now we're finally back in the main method, which was paused on this. It was waiting for execution for this to resolve. This resolved to 6, so resume execution right here. Assign 6, create a new variable, and assign result the value 6. And finally print 6 to the screen. So we computed geometric sum of 3. We computed 1 plus 2 plus 3. And we did through this recursive call and putting all these stack frames on the stack. Having them return, all return to each other, and finally returning back to the main method to get the result. Questions on this example? Is that fine? Is that too fast? Anything? I ripped it fairly quick, but a lot of it's repeating myself. Are we good on that? Any questions? Okay. Then our program ends. So in that code, we had a base case to our recursion. Once the conditional is false, we started returning 0, and we got to start returning back up the recursion. What if we didn't? What if we didn't have that? What's going to happen with this code? So now, instead of decreasing n until it's 0 and then returning 0 and returning back up, Now, what if we just keep making recursive calls? So with this code, let's jump to this part of the execution. This is where we would start returning, return 0 and start destroying stack frames, going back up the stack, start freeing up this memory again. But here we don't have our conditional, so we're not going to do that. Now we hit compute geometric sum of 0. We're going to put a new frame on the stack. With n equals 1, that's going to put another new frame on the stack. It's going to call this with -2. -2, that's going to call it -3. Eventually, we're going to hit the end of our stack space. We're going to get what's called the stack overflow, the namespace of our favorite site. We're going to try to access memory that has not been to us, and we're going to crash. Program crashes because we have more space than we're allowed to use. This is very bad. If you're writing, when we start writing recursive methods and you see a stack overflow error, it's only because you don't have a base case to your recursion. There's no condition in your recursion that will have it just return with a recursive call. A question?
Didn't you say on Monday that compilers can
Sometimes. So sometimes compilers can avoid the overflow, and specifically when it's something called tail recursion, which means the recursive call is the very last thing that happens in the recursive method. Since the recursive call is not the last expression in this method, we don't get to avoid that. Compiler can't help us out here. And unfortunately, we lose that out. Of course, as pointed out in the other lecture, worth saying, for this specific question, I mean, if I had a lecture question that said, write a method that computes geometric sum, you really shouldn't use recursion for it. This is much better suited for a loop. You would just loop over those values and track the sum. I just wanted to use some recursion here to show you a bunch of stack frames. If I use a loop, I only get to talk about scope. I want to talk about stack frames and putting a bunch of stack frames on the stack, having a whole bunch of variables named n, and showing that that doesn't matter because they're in different stack frames. Can't do that with the loop. That's the only reason we're using recursion for geometric sum. But you should use a loop for this. The loop is more efficient because it doesn't use all this space and memory. This is very memory inefficient. So let's go to the code, and I want to show something that I'll show examples of this on Friday as well, but I want to at least give a taste in the last 10 minutes here. First, let's run our Let's run our program. I claimed it should return 6, and thankfully it returned 6. Didn't make any big mistakes there. So what I want to show is called the debugger. The debugger can be your best friend when it comes to programming. It's a very, very powerful tool. We'll just use some of the basics in this class. Really, I just want to use it to show variable values. But this is something that can save you hours of debugging. When you have a bug in your program, you don't know what's going on, you're adding print statements all throughout your code and trying to read them all, the debugger can save you a lot of time in those instances. So let me show you how to use this thing. We're going to start by setting what's called a breakpoint. If you go in your sidebar here of your editor in IntelliJ and click, you're going to get this red dot. This is what we call a breakpoint. Now, instead of just running our program using the green button, or we could right-click over here, do the same thing. Instead of using the green button, the green go button, we're going to hit this debug button, this little bug icon. That's going to run our debugger, and what this does is it runs our code as though it were being interpreted, so it's going to run it line by line without the compiler efficiencies and stuff that might kind of jump things around a bit on us. But it's going to run our code line by line, and it's going to stop when it hits our first breakpoint. Or whenever it hits any breakpoint, it stops and shows us all kinds of information about our program. And specifically what we'll see today and Friday is all the values of our variables. And then I have this button here. This arrow is going to one step through the program, through the execution. So let me hit this to go into that method call. We just hit it a few times here. Let's get a little bit into this program. And when we look at all this information that it's showing us, excuse me, this is going to show us right here all of the stack frames on the stack. Our frames, this is our whole stack and all the frames that are on the stack. I can click each one of these frames and see all of the variables defined in that stack, in that isolated environment. So right here on this top stack, after I went through a little bit, I have a variable named n, it's of type int, and it has the value 1. If I look at one of my other stack frames, if I look at the second one here, the one that I'm currently in, here I have the value variable n, it's of type int, and has the value 2. If I go to the next one, it has the value 3. If I go to main, I can see I don't have any variables except my command line arguments. So I can see all of this information. I can continue stepping through this. Once I'm in the stack frame where n is 0, my condition is false, I'm returning 0, and you can see as I click through, these frames are going to start disappearing. They're going to start being popped off of the stack. They're going to start being destroyed. And eventually I get back to my main method and print out 6. I have that result 6. So anything that we did in these last 2 lectures when I'm showing the stack and the heap, you can run the debugger on any program that you have and see how the stack and heap are going to be handled, how those are going to work. So for this one, we can verify that all that stuff we did, it sure better be true. And if we go to our Stack Overflow example, let me run the debugger again. Start stepping through this. And here, since we don't have our conditional to tell us when to stop, to tell the recursion when to stop, we're just going to keep getting frames on the stack. We're going to frame after frame after frame until we get that overflow. So now what we can do in the debugger too, I have this one breakpoint in main. We're not going to hit that again. We're going to crash before we get back to main. So I'm going to hit this button here, this resume button, and that's going to restart the program and go until it hits another breakpoint. Since I'm not going back to main, I'm not hitting another breakpoint, and we'll get to see our program crashing. So I don't have any good information here, but I do get my Stack Overflow error. So I got a Stack Overflow error on this line. It was called from this line. It was called from this line. I can go back that whole stack trace. I can look through all the frames of this call, of all these calls. And I can see there were that many. I'm not going to count them. It's a lot. But there were that many calls on the stack. There were that many frames on the stack before we crashed. So we get quite a bit of memory in the stack. But if we start going infinite like this, we're going to use up, no matter how much we have, we're going to use it all up. And we're going to crash, or we're going to get the stack overflow. So let's do the same thing with BirdBox. Again, I'll just pick the first line of my main just so I can see everything that's going on. Let's, I did that specifically, did not do that. Debug, not run. And we can start stepping through this. We're going to, you can see when we create a new object, anything that's outside of the methods is going to run. If you want to set up code in there, you can put it there. All that code is going to run. It doesn't just have to be the state variables that you create. So if there is a need for something, some little more extra initialization that you want, feel free. Create that bird. Let's just get a few steps in so we have some interesting things to look at. Let's get past this line too. We'll see that this is going to go into each constructor. Runs all that code. And let's look at what we got at this point. I should have just set the breakpoint here, shouldn't I? So let's see what we got here. We have this variable bird, the very first thing that we created. We created a new bird, and I can see the variables here, but of course these variables aren't stored directly in the bird variable, we're only storing a reference. But if we look over here, we can tell if we have a reference or not. Right here, we see we have an object of type week3.memory.bird, and it's at the reference 587. And so that reference is how I can access those variables. And the debugger is going to that reference for me and showing me everything that's at that reference in heap space. So once you see this at something, that's in the heap. That's in heap space, where we didn't see that when we have ints and stuff. You can see technically, yes, strings are in the heap, but again, for this class, not going to worry about that too much. You can, but if you don't, there are more important things that we need to worry about for this class. Then when we look at the box, let me unfold this a little bit. This box, that's at 959. We have one bird at 587. That's the same exact reference as the object, the reference in the variable named bird is the same exact bird. There's no copies, nothing. We're just pointing to the same place in memory, and we're going to share these variables. These variables will always be the same because they're referring to the same object. So they could just happen to be the same 0 and 1 here, but those are the same because they're referring to the same bird. Then the second bird, 958, we have a different reference, completely different object, completely different bird, separate from the other bird in the program. And box 2, oh, I already mentioned that, didn't I? Call these methods, we go into each method. Times checked incremented for this bird, incremented for the other bird, and we reach the end of our program. And we got nothing in state and vote. That's everything. Any questions? Yeah.
Use the debugger for your test cases, or only on main method?
You can set breakpoints in your test cases and do the same thing. Highly recommend it.